Hi, in this video, we're going to build an I2c driver for communicating with a temperature sensor. The I2c is a communication protocol that uses two lines for data and clock signals. It is useful in connecting with multiple peripheral devices where the peripherals share the same I2c bus. These peripherals are distinguished by their unique addresses. We will open the I2c Studio to begin our project. We shall start off by creating a new Renesas RA6M4 project. Our chosen board is, as usual, the RA6M4. For rest of the configurations, we keep them at their defaults. We will then choose the bare metal minimal option. Once we click Finish, the project files will be initialized. Our first task would be to add a new stack for the I2c communication. This stack would allow us to configure the I2c channel from the Properties tab. First, we would assign channel 1 to this stack. When channel 1 is selected, the clock and data pins are already configured at pin 511 and pin 512. The circuit for demonstration requires 4 wires, 2 for power and ground, and 2 for signal and data. The wires from the sensor can be inserted into the relevant pins of the microbus port on the EK board. The clock pin is labeled as SCL and the data pin is labeled as SDA. On the sensor side, we are using the Hs3001 humidity and temperature sensor module from Renesas. The data, clock, and power pins are located between pin 3 and pin 6. Coming back to the properties configuration, we shall name the channel Master 1. We will also enter a name for the callback function. The callback function is called after a successful I2c communication event. Once these are done, we can generate the project contents. We will start coding from the hullentry.c file. We can enable a better view by selecting the C++ perspective. The first order of business is declaring the variables to be used in our program. We will declare the I2c event variable. Once that is done, we will declare an empty 1-byte unsigned integer array consisting of 4 elements. This variable will hold the data received from the sensor module. Next, we will add 8 variables to hold the various parts of the humidity and temperature reading. We will have 4 2-byte integer variables to hold the decimal and integer part of the readings. We will also have 4 additional variables to hold temporary data while processing the humidity and temperature readings. The I2c master event is a custom data type that comes with the I2c API and accepts the different status values that may be generated during an I2c communication. We will then declare the function prototypes for the various operations of the I2c module. There are 2 functions for initialization and deinitialization of the module, and there is the read and write operations. Each of these functions involves calling various APIs and error handling for successful data transfer. Designing these functions basically constitute designing the I2c driver. The first of these functions is the initialization function. We can name it I2c master init. The first step is to define an FSP error variable which holds the return value for the FSP API calls. Then we are going to utilize 2 I2c APIs. One to open the channel, the second to set the slave address for this channel. The slave address is passed to this function as an argument. We can find the necessary API calls from the developer's assistance menu. For each of these calls, we will implement the assert macro to ensure the API calls have executed and returned an FSP success status. At the end of this function, we shall return the final status of the API calls as function return. For the next function, which is to deinitialize the module in the event of an error in the I2c communication, we will implement the close API. Now, this API needs to execute successfully in order for the rest of the program to run smoothly. The write function will consist of the I2c write API and additional error handling conditions to ensure smooth transfer of data. This function also returns an FSP status and accepts two arguments, the length of the data in bytes and the actual data to be transferred. First, the I2c event variable is set to 0. Then, the write API is executed. If this execution is unsuccessful, then the module will be deinitialized and the error status will be returned by the function. We will also add a timeout routine of about 1 second and wait for the transfer status to be complete. If the status is not complete, that is 0 value for the I2c event, the module will deinitialize and return a timeout error. Next, if the execution is complete but the transfer is not successful, then the deinitialization routine will be called as well. Once these checks are done, a final FSP status will be returned by the function. The read function is quite similar to the write function. It takes in the argument on the length of the data to be read and the address to store the data. Similar to previous write function, some error handling and timeout operations are conducted. These four functions will act as the I2c driver for this project. In order to perform an I2c operation, we are going to use one of these functions. Next, the callback function definition template can be found in the developer's assistance menu as well. In this function, we're going to update the I2c variable with the event status. We can now move on to writing the code to run in the main function. First, we will declare the FSP status variable and then we will initialize the 1 byte single element array to hold the transmit data. Then, we will call the initialization function and pass the slave address of the sensor module, which is a hex value of 44. Then, we will send a byte of 0 values to wake up the sensor. For each of these cases, we shall implement the assert macro to verify the FSP status. Then, we will create the while loop to run. To start the measurement, we will need to send a byte of 0 values once more. This would trigger the sensor to return temperature and humidity readings. We need to add a short delay for the sensor to stabilize. Once the request has been sent, the read function will be executed to read the 4 bytes of data that has been received. For this sensor module, the first 2 bytes contain information on humidity and the third and fourth byte contain data on temperature. For humidity, the information is contained in the first and second element of the reception buffer. We need to perform some processing on these data to extract their values for relative humidity. The final value produced will be a value that is 100 times the actual value. So, we can perform a division and a modulus operation on this value to extract the integer and fraction part. For temperature, We are interested in the third and fourth element of the reception buffer. We shall perform some processing on these data to extract the values in Celsius. Similar to the previous data, the final value produced will be a value that is 100 times the actual value. So, we need to perform a division and a modulus operation on this value to extract the integer and fraction part. We will add a 500 millisecond delay before the next read request is sent. So that's about the program we need to write to extract the relative humidity and temperature in Celsius. We can now build and upload the program. We do so by selecting the build option first, followed by the debug option. Once the program is running in debug mode, the perspective will change to debug and we can access the expressions view, which shows the values of the variables of our interest. We can add the variables that hold the integer and fraction part of the humidity and temperature and enable real-time refresh. This will refresh the updated readings as soon as new value is received from the sensor. So that is a simple demonstration of designing an I2c library and using it to read values from a temperature and humidity sensor with an RA microcontroller.